Have you ever watched an AI play a game with, basically superhuman skill and just wondered, how? How on earth does it know the perfect move to make when there are more possibilities than atoms in the universe? Well, it's not magic. It's actually this really elegant process of trial, error, and improvement. And today, we're going to break down that secret sauce and see exactly how a machine learns to find the single best path to victory. So this is the big question, right? You can't just write a rule book that covers every possible situation in a complex game or in the real world. It's just not possible. So how do you build a machine that can create its own winning strategy? Well, it learns through experience. And by the end of this, you're going to understand exactly how that process works, right from the ground up. So here's how we're going to break it down. First, we'll define what an AI strategy even is. Then, we'll set up the rules of the world it's playing in. From there, we'll see how it grades its own performance, how it uses that grade to get better, and finally, we'll see how this powerful idea shapes the AI we see all around us. All right, let's dive into section 1. Before an AI can get better, it needs a starting point. It needs some kind of plan, even if it's a really bad one at first. And in the world of AI, that plan, its current strategy guide, is called a policy. At its core, a policy is just the AI's rulebook. It's super simple. If our robot is in a specific location, which we call a state, the policy tells it which move to make. That's the action. It's the basic logic that answers the question, okay, given where I am right now, what should I do next?
Now, these policies can come in two main flavors. A deterministic policy is like a strict command. From this spot, you always move right, no exceptions. But a stochastic policy, well, it plays the odds. It might say, from here, there's a 70% chance I'll go right, but, a 30% chance I'll go up. This little bit of randomness is actually super important for letting the AI explore and maybe discover new, even better paths.
Okay, so our AI has a strategy, but a strategy is kind of useless without a world to use it in. To learn anything, the AI needs a map of its environment. It needs a clear definition of the game board and all the rules of the game.
In reinforcement learning, we model that world as something called a Markov decision process, or an MDP. I know, it sounds super complicated, but it's really just a formal way of laying out all the pieces of the puzzle nice and clearly. An MDP breaks the world into 5 key parts. You've got states, which are just all the possible places our robot could be. Then actions, all the possible moves it can make. Transition probabilities basically define the physics of the world. Like, if the floor is slippery, trying to move right might only work 80% of the time. Rewards are the points you get, like +10 for treasure or -5 for a trap. And finally, the discount factor. This one is crucial. It controls whether the AI is short-sighted and just grabs quick rewards, or if it's far-sighted, aiming for a bigger prize way down the line. So we have a strategy, and we have the rules of the world. Now, the learning can actually begin. The first step isn't to change anything. It's just to figure out how good or, how bad our current strategy really is. And this critical step is called policy evaluation. Think of policy evaluation like creating a score map for our maze. For every single square, we're going to calculate a score or a value that tells us how good it is to be in that spot, assuming we stick to our current strategy. A square that leads to treasure will get a high score, and one near a trap will get a really, really low one. And here's the core idea. The value or the score of any given spot isn't just about the reward you get for landing right there. It's that reward plus the value of the next spot you're likely to end up in. This is what connects the whole map together, creating this ripple effect where the high value of the treasure kind of spreads backwards through the entire maze.
So how is this score map actually calculated? Well, it's all about iteration. The AI starts with a completely blank slate, maybe assuming every spot has a score of 0. Then it just sweeps through the map again and again and again, updating each square's score based on its neighbors. It keeps doing this until the values stop changing much, and what it's left with is a stable, accurate score map, a final grade for its current strategy.
Okay, grading our strategy is a huge first step,
But it doesn't actually make the strategy better, does it? For that, we need to complete the loop. And this brings us to the path to perfect, a super powerful algorithm called policy iteration.
Policy iteration is really where the magic happens. It's a simple, powerful two-step dance that, and this is the incredible part, is mathematically guaranteed to find the single best strategy for any given problem.
So it all comes down to this two-step loop. First, you run policy evaluation to create that score map we just talked about. Then comes step 2, policy improvement. You look at your map, and for every single square, you update your rulebook. You just say, from now on, I'm taking the action that leads to the highest scoring neighbor. You just act greedily, based on your new knowledge.
And then what? You just repeat the process. That's it. You evaluate the new, improved policy to generate an even more accurate score map. Then you improve the policy again based on that new map. You just keep doing this dance, evaluate, improve, until the policy becomes stable and it just doesn't change anymore. At that point, congratulations, you've found the best possible strategy. So how do we know this process won't just go in circles forever? Well, it's thanks to something called the policy improvement theorem. This is the mathematical guarantee that with each loop, the new policy will be strictly better than, or at the very worst, equal to the old one. You can never get worse. You are always step by step climbing uphill towards the optimal solution. This evaluate and improve loop is such a foundational concept in AI. So let's take this elegant theory and connect it to reality. Let's look at where it's actually used and, just as importantly, what its limitations are. You can almost think of it like the tortoise and the hare. Policy iteration, that's our tortoise. It takes these big, slow, but really thorough steps. It fully evaluates the policy each time, so it needs fewer loops to get to the finish line. Value iteration is the hare. It takes many, many more steps, but each one is way faster, combining a little bit of evaluation and improvement in each go. Which one's better? It totally depends on the problem you're trying to solve. And this logic goes so far beyond just mazes. It's the engine humming inside robotic navigation systems. It's the strategic mind behind game-playing champions in chess and Go. And it's the optimizer for everything from financial portfolios to complex factory schedules. All of it is built on this core loop of evaluation and improvement. But, this approach isn't a silver bullet. It has a couple of big catches. First, it requires a perfect model of the world. You have to know all the rules in advance. And second, it really starts to struggle when the number of squares on the board becomes astronomical. And these challenges are precisely why newer, more advanced methods had to be created.
And that right there is the key takeaway. Because even though modern AI uses much fancier techniques, things like Q-learning or deep reinforcement learning to get around those limitations, they are all built on this fundamental idea. At their heart, they are all just more sophisticated ways of doing this exact same beautiful dance. Evaluate your strategy and then improve it.
So as we close, just think about that simple, powerful loop. Grade your current approach, find out what works, and then make a greedy change to do more of it. It's this fundamental principle for learning that applies to machines, to businesses, and even to our own lives. So I'll leave you with this. What complex problem in your world could you start to solve by applying that same elegant logic?